Hey everybody, today I'm going to explain a little bit what saturation means when it comes to a transistor, and we're also going to do a calculation for a saturated transistor. Normally, what we have is a formula, beta equals IC over IB. And what that means is that for any given transistor, it would have a beta, and the beta gives us the relationship between the current flowing through the base circuit and the current flowing through the collector portion of the transistor. Often beta is 100, which would mean that 100 times IB, or the current through the base, would be what your current through the collector would be. Now, saturation means that at some point, you just can't sustain this. So you can keep reducing the size of the resistor in the base, which means the current would go up, but there just isn't going to be enough voltage to give you a proportional current through the collector. So let's look at this. The ratio of beta is the current flow through the base, and it's proportional to the current flow through the collector, except when the current reaches saturation, beta no longer becomes true. And that means that at saturation, increasing IB no longer increases IC. Let's look at this little example. I've got some givens here. I've given you a power supply of 20 volts. Beta, we're saying, is 70. And my load is 100 ohms. And my base resistor is set at 1,000 ohms. So those were your givens. Remember, this is an NPN type transistor because the arrow is pointing outwards. This lead is called the emitter. This one's the base, and this one's the collector. We have two circuits. If there is current flow flowing through the base in the outer circle, then current flow will flow through this junction of E to C and up through my load and back to the positive. We can solve this. So what we're trying to determine here is whether or not the voltage here is actually realistic. If it's not realistic, we know that the transistor is saturated, and even though there's a ton of current flowing through the base, there's just not enough voltage supply to supply the current flow through the collector, through the load. So normally I would solve, you just go about solving it normally, and we know that typically there's 0.7 volt drop from emitter to base. So 20 volt supply minus 0.7 would give me a 19.3 volt drop across RB. So EB is 0.7 volts. That's this voltage in here. The supply minus 0.7 gives us 19.3. That's the voltage at RB. To find the current at IB, we just use Ohm's law. So EB divided by RB, so 19.3 divided by 1,000 gives me a current flow of 0.0193 amps through RB. The next thing we can do is take beta, the beta that was given, and it was 70, so beta typically equals IC over IB, and if this circuit is not saturated, it will come up with a voltage here that is something less than 20 volts. If it's saturated, the voltage here at the load would be unrealistically high. So I can take my 70 times my 0.0193, and my IC would be 1.351. 1.351 is the current flowing through the load. The last thing I do is use Ohm's law, current through the load times the resistance of the load. should equal the voltage at the load. So 1.351 times 100 gives me 135.1 volts. 135.1 volts. Now what I do is I compare these two. I compare the supply to what this calculation has given me. And I realize that that's not a realistic number. I don't have enough voltage there to give me 135.1 volts there. So in reality, it can't be that number. So I cross it out, and what I do is I say that circuit is saturated, meaning that I have a ton of current flowing through here and just not enough voltage to proportionalize the current flowing through there. When a transistor circuit is saturated, the actual voltage at EEC is 0.1 volt. And that's just the minimum voltage that can be dropped across that junction and still have the transistor working. So if there's 0.1 volts across there, and we have a 20 volt supply, then we would know that 20 minus 0.1, this actual current flow up here would be giving us a 19.9 volt drop across here. So our actual voltage and current would be 19.9 divided by 100, or 0.199 amps. And the relationship between beta is no longer true. So to recap, E load cannot be 135.1 volts because our supply is only 20 volts. And at saturation, the actual voltage across E load will be the supply voltage minus 0.1. The 0.1 volt is across ECE, and it's the minimum voltage that we need to operate that transistor. I really hope that was helpful, and enjoy the next video.